So the last conference was 6 days about McMullen Algorithm implementation for a Shotty group. Alejandro Ucan is a student of PPCAD and Ucan.
So I want to thanks to the organizers to invite me to give this talk. The aim of this talk is just to present the McMullen algorithm to compute the Hausdorff dimension for Schottky groups. And in 1997, McMullen introduced an algorithm to compute this Hausdorff dimension and apply it to compute the Hausdorff dimension to Julia sets for a family of polynomials and a family of rational maps, and for compute the dimension for limit set of Fuchsian groups. So, what is the Hausdorff dimension? So we start with a subset of the n-dimensional Euclidean space. Have to be a Borel subset and fix a real number, a positive real number. And for an epsilon, a positive number, we can, for every cover of balls of the set, we can define a number that is the sum of all the radii of this ball of cover of balls. And if we take the infimum over all the countable coverings, we obtain this number. And if we tend this number to, as epsilon tends to 0, we obtain the Hausdorff measure of the Borel set, that is this. So this is the this measure has the property that could be infinite, but there is a number that for every lower number than the privileged one, the alpha Hausdorff measure is infinite, and for greater numbers are 0, and this number is called the Hausdorff dimension of the subset. So now we know how is defined the Hausdorff dimension. Where we will apply the McMullen algorithm. We will apply it to the Schottky group, and how we construct a classical Schottky group. So we take an even number of circles in the Riemann sphere. We will ask for these circles have the disjoint interior, and the half number of Mobius transformation that pair these circles. How will be the pair? It will that the complement of one circle would be in the inside of another, and the complement of the other circle will be in the interior of the previous one. And the group generated by this transformation is called a Schottky group. In particular, the Schottky groups are free, in this case, and it's a Kleinian group, and if it leaves a circle invariant, is called a Fuchsian group. So an important dynamical feature of the Kleinian groups is called the limit set. That is for a Kleinian group acting on the Riemann sphere. The limit set is just the set, the closure of the cluster points of orbits of points in the Riemann sphere. And we know that the complement of this limit set is the domain of discontinuity, and is an open maximal open set where the action of the group is properly discontinuous. So we have the ingredients to apply the McMullen algorithm. So where we start? So we have the unit circle, and we will ask for 4 even number of circles orthogonal to this unit circle. And we will ask for the reflection of these circles And if we took the first one and apply the reflection to the second one, the C2, we obtain an image of C4. Maybe. We obtain a little circle inside the C1. And if we continue, we obtain the whole 3 circles outside this C1 inside C1. So we can continue this process for every circle. And we can see that if we continue doing the reflection of all over the circles, the limit set will contain in all the image of these circles, the little circles. So if we could if we could bound this shrinking of the circle, we can calculate or approximate the Hausdorff dimension because we just need the covering and how this covering shrinks. So how is the algorithm? So you need a partition. In this case, would it be the interior of the circles and the reflection, and you need privileged points that will be called sample points. So for every this is a misstatement, sorry. You will choose, the first step is you will choose numbers in the interior such that the image of the numbers has to be the sample points. So the next step is you have to compute the transition matrix. That is, this matrix, how is computed? So for every pairing of these circles, you will put a number. So this relation is, you will put, we will say that the CI circle and the CJ circle are related if the measure of the pre-image of the reflection I of the circle J intersection with the circle I is greater than 0. And the number is just the inverse of the absolute value of the derivative of the reflection evaluated in the points that you found in the previous step. Why this? Because the inverse of the derivative of the reflection, this number, in particular, the derivative is bounded above by a number greater than 1 in the interior of all the circles where the reflection is defined. So this matrix has all the combinatorics inside them. So what is the next step? You have to solve for a special number epsilon greater than 0 the spectral radius of the matrix T alpha. And what is the matrix T alpha? Is just power every entry to the alpha. Then this alpha is an approximation of the Hausdorff dimension, and you can do a refinement of the partition where you start and repeat all the process. Properties of this algorithm is that you just need the combinatorics of the partition. For most of the dynamical systems, the transition matrix is primitive, so you can use the Perron-Frobenius theorem. And if you need approximate the Hausdorff dimension to n digits, you have to do a n number of refinements of your initial partition. What is a bad part of this algorithm is that for the previous Schottky image, the Schottky group, for this, if you do a n refinement, the transition map matrix has 4 times 3 to the n minus 1 squared entries. And is sparse. But to calculate these entries, you need a big computation in the program. So it's a bad thing. For example, is you calculate for a refinement is maybe 20,000 entries and something like that. So this is the algorithm, and for the experts, this partition is called Markov Partition. So it's for those who know. So I bring some examples, but my computer, it doesn't work with the HDMI, so I don't know how to. I will show you the algorithm, but for the algorithm that I did works for pair of bands, that is 3 circles, and these circles are has center and radius. This has center in this is the center, as this is the radius. W is a cubic root. Of minus 1. So, and theta has to be lower than 1/3, P/3. And the Hausdorff dimension for this 5 times pi/9 is something like 0.55 and a lot of numbers. And for the other examples are the symmetric theta Shotky groups. Where is a similar construction. The center are in sec of theta plus W and radius tangent of theta, and W can be 1, I, minus 1, and minus I. And it is symmetric because the radii are the same, as you can rotate P/4 rotation, and you continue in the same circle. It's invariant, and the theta has to be lower than P/4. And another example is a non-symmetric Schottky theta Schottky group, and this is something similar to the centers are in the same. I minus 1 minus 1, and the center are in sec. You now need 4 angles. And you have 4 TID. And theta 1 plus theta 2 plus theta 3 plus theta 4 has to be lower than pi. And in our example, I can compute in just my laptop that is a easy laptop, and up to 8 digits. It is the most accuracy that I can do. I don't know what to do. If I could show you the algorithm, I can do it, but I can't. Tomorrow, maybe tomorrow. That's it. Thanks.
Have you tried the formula by Rouen?
Rouen.
Thermodynamic formalism.
No.
There's an explicit formula to compute it, and also school from Texas, Dental Texas, to compute it. And you know the theorem says that the half dimension varies real analytically.
Yeah.
And there's one way to compute it using este. But of course, coming from McMullen means that it's not easy. No? But still, maybe interesting.
Yeah, it's a really easy algorithm because you just need to compute, and that's it. You just put the initial partition, and the algorithm do it everything. Calculate the sample points. Well, you put the sample points and calculates the GYs and do refinements and accurate up to 8 digits.
No, but I mean to have the exact formula in terms of the centers of the circles and the radii would be beautiful. I don't think that has ever been done, or whether it is even possible, probably not. But it's interesting.
¿Cuántos refinamientos has podido hacer y cuál es tu velocidad en la computadora? ¿Cuál es el tiempo que te lleva?
Ok. Puedo hacer 8 refinamientos. Porque para hacer el refinamiento, por ejemplo, si necesito hacer el refinamiento 7, necesito ir en la longitud de árbol 8, porque necesita preimágenes. Y el tiempo, no, menos de 1 minuto. O sea, el algoritmo está hecho en Python, no tarda mucho, y el número de iteraciones que necesita para calcular, para aproximar la dimensión, varía entre 10 iteraciones hasta 350 iteraciones. Y
la longitud de la matriz de transición, la dimensión,
si tienes 4 círculos, es 4 por 3 a la n-1. Y es la profundidad que tú quieres. Es la aproximación de n dígitos. Si quieres 3, pues es 3 por 2.
Si quieres 64.
Pues es muy exponencial. Aunque la mayoría de las entradas es 0. Lleva mucha memoria solo por ser ceros.
More questions? Thank you, Alejandro.
Thank you.